Hello, guys. This is Stefano Rini, professor at NYCU Taiwan, currently visiting Polytechnic of Milano in Italy. I'm going to be here for 4 months. And I'm here to briefly introduce to you the PhD course on quantum machine learning that I will be teaching in September. So here is a brief introduction to the course so that you can decide whether you're interested or not. So yeah, just a brief introduction to the course and some motivation why you should be taking the course. So the idea is that quantum ML, it's a topic of growing interest that lies at the intersection between quantum computing and machine learning. And the topic seeks to answer the question, if someone gives to us a good quantum computer, what type of machine learning problem can we solve now that we are not able to solve with classical computers, and how you will achieve such a feat. So the previous Venn diagram made it look very simple, made it look as if there were only two topics there. But actually, the current literature has already explored a few topics, right? And I put them here in the slides for you. For example, in the first slide, in the first row of this Venn diagram, you see that in machine learning, people talk about simulated annealing as a methodology for solving optimization problem. In quantum information processing, people talk about quantum deep sampling in order to generate samples from a certain distribution. And if you apply one to the other, then you will get the intersection of the two topics, which is quantum annealing, and so on and so forth, right? So you can take a look at these slides, and you can see a little bit what are the topics of intersection that are of interest to you. Notice that we switch left and right from the Venn diagram above, but I want to read to the slide, so bear with me. So let's look at the left side of the Venn diagram with respect to the original simple slides, and let's see a little bit what quantum computing generally deals with. Before we do that, let's look a little bit of a brief history. So Feynman was the first one to propose an idea of using quantum mechanics principle to perform computations, to create machines that will be able to perform beyond what classical physics can predict. And Feynman famously said that I think I can safely say that nobody understands quantum mechanics, and he was trying to embody this idea that quantum mechanics, it's very unintuitive for us humans that we live at the scale of Newton interaction and try to imagine a much smaller scale of interaction, which is the quantum scale of interaction. So Feynman in 1982 envisioned this machine that you was using quantum mechanics to perform computation. In 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universals. This parallels the result from Turing, right? And the Turing machine that was shown to be universal. In 1994, Shor comes up with a quantum algorithm to factor a very large number in polynomial time. So in 1994 was the first time that we saw this very counterintuitive algorithm that was able to perform what would be an exponentially complex operation in the classical domain to become of polynomial complexity in the quantum domain, and we will explore this topic further. And Love Grover develops the quantum search algorithm that is able to perform a search with a complexity of a square root of n. So again, another example of an operation that performed in the quantum domain presents much lower complexity than the same operation performed in the classical domain. So let's delve a little bit deeper on the difference between classic and quantum world, so we can discuss the rationale behind our interest in the quantum world as engineer, communication engineer, and electrical engineer more in general. So in classical computation, we are all familiar with the idea of a bit. A bit is something that can take only two values, either 0 or 1. In the quantum domain, instead of having this minimal unit of information, we have the minimal unit of information, which is the qubit. And the qubit is the coherent superposition of two simultaneous states, generally, the 0 state and the 1 state. And the superposition is with coefficients alpha and beta, such that alpha squared plus beta squared is equal to 1. And the representation of the qubit, it's here on the block sphere on the right. And you can see now that a single qubit expresses the linear combination of the two states, and so it has an inherent richness which goes beyond the one of the classical bit. Okay, so now that we have understood what is our minimal element of information, then we can move to the next step, and the next step will be to construct gates. Okay, so here on the left of the slides, you see the classical gates that we are very familiar with from our early classes in computer science. So you have the NOT gate, the AND gate, the OR gate, and then so on and so forth. Quantum gates are much more involved, generally speaking, because due to the nature of quantum physics, if we had a many-to-one mapping, then this will correspond from a physical perspective to a destruction of information, and the destruction of information will result in a general output. So not all possible operation of the qubits are meaningful in a physical sense. The only one that have sense are the reversible one. So the operators that we're going to look at are going to be reversible operator. And I put a couple of examples here of a Pauli X gate, a Pauli Y gate, a Pauli Z gate, and another gate. And we're going to see further example of these quantum gates. Okay, so we went from the unit of information to a first processing through classical quantum gates. And then once we have established these minimal logical entities, then we can build upon this logical entity in what we will call circuits. So now we can compare classical circuits with quantum circuit. So in a classical circuit, you will have some sort of combination of the logical operation before, and what you will obtain will be a deterministic output of the circuit inputs. Not so in quantum circuits. In quantum circuits, what you are manipulating are quantum states. And in order to observe the quantum states, you have to take what is called the measurement. This is what is indicated generally with this little indicator, like, I don't know, a speed indicator like symbol. And these measurements are stochastic measurements, meaning that we observe a distribution of the support of the output. So inherently, the output of a quantum circuit is not going to be a deterministic quantity. It's going to be a stochastic quantity, so that we have to perform repeated measurements to observe a certain distribution of the output and infer something about the quantum state of the circuit. Okay, very good. And then once we started with the unit of information, then we had gates, then we had circuits. Once we have circuits, we want to build specific circuits that perform a certain set of algorithms. And this is where the meat of the interest in quantum algorithms is, because generally speaking, people are interested in quantum speedups. So you want to come up with an algorithm, invent an algorithm that performs an operation on either classical or quantum quantities that can be performed at a fraction of the time or the resources required by a classical computer. Okay, so either you perform the same operation with a lower complexity in terms of time, or the lower complexity in terms of number of gates. And this is what people call quantum speedups. And there are many examples of quantum speedups. You can go to this nice website which is called Quantum Algorithm Zoo, and there you will find a host of algorithms in which you can determine the speed up of a certain quantum algorithm. Okay, very interesting. And then the goal that we have is that of a quantum advantage, right? So we want to find an operation that cannot be feasibly performed with classical computers and can only be performed with a quantum computer, and this is what we call quantum supremacy or quantum advantage. Okay. So as we were saying, quantum speedups are characterized either in terms of query complexity. So we measure the number of queries from the algorithm to the information source for the quantum and the classical algorithm, and a speedup is in terms of the number of queries to the information source to come to the correct answer. Or it could be a supremacy in terms of gate complexity. So we look at the elementary quantum operations or gates that are required for both, and we figure out that one algorithm, let's say the quantum algorithm, requires much fewer resources than the other one. Now we have to come to sort of the sticky point, which is the fact that quantum computers, from a technological standpoint, are not here yet. Okay, so there is a lot of investment, there is a lot of interest in both, mostly in academia, also from the point of view of companies in producing quantum computing and furthering quantum technology. But the reality is that this is not real. It's not here yet. So there is no real quantum computing right now, or for any foreseeable future. There is no established technology. People are still trying to decide whether trapped ion or superconducting qubits. The computers that we have are not really fault tolerant, so we have to spend a lot of energy in designing fault tolerant mechanisms for quantum computing. There is not really an effective way for communicate, store, or regenerate quantum states. So quantum states are very delicate states that it's currently very hard to store in any meaningful information. Even having a computer with very few bits costs some millions and millions of dollars, and there is generally a need for a large set of hardware developments in order to make this technology more readily available to humanity. So these are personal opinions. So I try to be fair, but of course these are my personal opinion. And so the idea is that what should we do as engineers, and why should we be interested in this? And my perspective on this, again, personal perspective, is that we are anyway hitting the technological limit in which quantum effects will play a role. So, for example, if you look at the semiconductor fabrication, we are already at the 2 nanometer limits. Whatever happens below the nanometer scale will undoubtedly suffer from quantum effects. And there are some already sort of ready to engineer interaction that are not fully quantum and not fully classical effects that occur for a quantum system that we take advantage of. By this I mean that there are some quantum effects that we can observe, for example, like quantum interference for photonics, that one can explain with some very simple engineering rules that are reproducible in some sense, that one can take advantage of without having to think of a full implementation of a quantum computer. And generally, the type of technological and academic advances that are required to further quantum computer technology is something that will be interesting, will be beneficial for our society, even if the realization of a full quantum computer is, let's say, 10 or 20 years in the future. And I always like the quote that a society grows great when old men plant trees under which shade they know they shall never sit in. Okay, so we do things also for the future that shall come, even if we are not in the future. Okay, so we discussed a little bit quantum computation. So let's move to the right side of the Venn diagram, which is that of machine learning. Of course, there is not much that we need to say about this. We are in the throes of a machine and deep learning revolution. You cannot let a day pass without some new AI development, even if you try to escape them. And this will be, of course, the decisive technology of this century, as firewalls, agriculture, metal smithing, steam power, flight, whatever you want to compare it to, right? So, and maybe also all of them together. So the scale of this revolution is completely unimaginable to us, and we cannot imagine what will happen in terms of AI developments in 1 year, let alone in 10 years. Okay, and given the state of things, it's nice to look at some nice figure for machine learning. So generally, people consider machine learning in this type of perspective, in which we put the evolution of machine learning in a time scale where initially people were talking about artificial intelligence, So the people were trying to reproduce human behavior, intelligent behavior in machines. Then in the 1980s, the statistical machine learning started to flourish. So people understood said that some classical algorithms for regression, for classification, for prediction. And then after the 2010s, there was the explosion of the deep learning technology. So deep neural network became the dominant paradigm for learning. I noticed that generally people recognize this sort of inclusion between artificial intelligence being more general, machine learning being a subset of artificial intelligence, deep learning a subset of machine learning, and now arguably we could say that generative AI is a subset of deep learning. Another cute slide is like this, right? So some of the names here of the development of deep neural of machine learning, and notice that there are these two slices, right, in the 1970s and the 2000s that are recognized as the neural winter or the winter of machine learning, because there were sort of long period of time, decades maybe, in which no significant progress in machine learning occur, and the science was sort of stuck, and then the floodgate opened again, and there was a very great advancement, and then the doors closed again, and so people recognize sort of the ebb and flow of contribution in the field, and people sort of expect that maybe some other winter of AI will come. Maybe NLP and application to NLP and generative AI will be the plateau of the technology after the 2020s. So it's a future that we're all here to witness, and we are very interested in witnessing, right? So as we said, first and second AI winter. Now we are a breakthrough in LLMs and generative AI, and now we are at the point in which we are trying to imagine what will be the future, right? Either we have a complete breakthrough with generative AI, and we get to a fully artificial general intelligence, so having a machine or a machine learning algorithm that can implement what is substantially the capabilities of a human brain, or we're going to stay on incremental progress in which we take the current advances and try to embed them in our everyday life. And we see the slow change in our world due to this deeper and deeper embedding of this technology. Or maybe we're going to have a third AI winter in which progress will stop. LLMs will be the best that we've ever seen, and nothing more will happen. And so this is the future that we are here to witness. Then, generally speaking, this is the slide that I prefer the most, all the cute slide that I presented here, which is the hype cycle for emerging technologies. Okay, so generally you can have this curve to different fields. Okay, and this slide is in particular for the AI field. So there is what's called an innovation trigger. Then there is then a peak of inflated expectation. Then there is the throat of disillusionment, and then the slope of enlightenment, and then the plateau of productivity. So of course, when innovation first comes, there is a lot of breakthrough and attention to this. Then there is a peak in which the hype is solid, and the hype pervades all different strata of society. Then people realize what are the limits of the technology, and they become negative. And then as time passes by, then everybody becomes more realistic about the potential of a certain technology. And here we see different data points, right, in the graph according to the writers, and we can see a little bit what is the expected time, let's say the imagined time of plateauing of this, right? So, for example, artificial general intelligence is something that people thought of when in the first stage of the innovation trigger, but of course, artificial general intelligence could be 10 years away, where there are different ways of imagining how this could be a reasonable timeline for AGI. For example, Edge AI, right, is something in which you imagine that your mobile phone will be able to access this very complicated model, for example, at the base station when you use your mobile phone. For example, 5G is another point at the hype cycle. We imagine that 5G will be fully enabled by machine learning. And then you can see a little bit the different technology, at which stage of this curve they are. And I think very rightfully, the writers of the article, they put augmented reality in the throw of disillusionment, right? Because people try to play around with augmented reality now for 20 years. There was a lot of, it started in the hype period, and it was a peak of the hype of augmented reality. And now we are really at the level in which the technology is mature. We understand what are the limits. We understand what are the potential of the technology, and now we just have to keep developing and pushing this in the plateau of productivity, right? When the technology eventually will go from an unrealistic expectation of the potential technology, either overhyped or underhyped, to the level in which it's a normal technology accessible to us. So it's useful to think about this in terms of the latest development of machine learning, because we are clearly in the peak of the hype, and it is somewhat hard for us to understand, to realistically address what are the potential of this technology in the future. So we can imagine what will happen after the hype cycle, in the slump period, in the trough, what we're going to find. It's possible that we're going to reach a plateau in terms of development of AI, maybe because of power consumption, energy dissipation. It is very much possible that if we don't find a smarter way to train these models, this model will become so power hungry that they will just require all the energy that we can produce already now. I think it's very well understood that the power consumption of these giga centers where Amazon runs these large LLMs for OpenAI, they are making the electric network very unstable. They are consuming as much electricity as a small nation. Maybe we will run out of time of training data. Maybe training will take too much time. Maybe training will take too much resources, so that for training the next generation of LLMs, we have to take every computer in existence and just put it there in training for months and months and months. And or maybe the product won't be able to have any incremental advance in the processing speeds, right? So that we cannot, let's say, speed up the training because we run out of, let's say, silicon technology for running things even faster. And this is when quantum computation will probably provide a venue for overcoming these obstacles. So just to give you an idea of the type of topics that we will cover in the class, we can focus on acronyms, right? So we're going to talk about KNN. So K, nearest neighbor, linear regression, robust regression, principal component analysis, support vector machine, random forest, decision trees. And these are classical machine learning methods, to which we can add some cute other names such as bootstrapping, boosting, bagging. And then we can think about deep learning. We're also going to cover deep learning in the course. So deep neural network, divided into supervised and unsupervised learning. The taxonomy goes on and on and on. And for deep learning, the type of acronyms that you expect are going to be DNN, deep neural network, convolutional neural network, long short time memory, variational encoder, knowledge distillation, and cute names such as transformer, attention, diffusion, and so on. And so now we discuss quantum computation, we discuss quantum machine learning. So let's see what we can expect to see in the course regarding the intersection of these two terms. So we expect quantum computer to perform classical compute in ML task. This, as we said, is the motivation that we have. This is because quantum machine learning explores the design and implementation of concrete machine learning algorithms that leverage quantum computers. And some of the example of this will be the comparison between BLAS and QBLAS. So BLAS stands for basic linear algebra subroutines. If you have ever had to deal with with a GPU, then you know what BLAS is. So many machine learning algorithms, they rely on linear algebra speedups that you can achieve with a graphic card, with a GPU, for methods like DNN, gradient descent, Newton method, PCA, linear regression, robust regression. And if we look at the quantum implementation of these algorithms, there are many instances in which the speed up of a quantum computer will allow us to perform this computation at a fraction of the complexity, as we said, either in terms of time or in terms of gates. And for example, the classical example is the fast Fourier transform. So if our sample size is 2 to the n, then the class FFT takes big N log n, which in this case will be n 2 to the n. And magically, right, the quantum algorithm that produces the same FFT transform only takes n squared. So here we save a polynomial factor in complexity. And you can imagine that this polynomial factor is not trivial if you think about, for example, a DNN training, in which you have to perform maybe tens of thousands of iterations, each involving millions of parameters. Of course, polynomial increasing complexity is a polynomial decreasing complexity would be a terrific boon. And in quantum ML, there are already quantum versions of many algorithms, such as K-means, Q-means, SVM, PCA, and so on. And in practice, achieving this type of speed up for for classical machine learning tasks using quantum computers would be absolutely a practical relevance. Will have absolutely practical relevance. When people talk about quantum machine learning, people imagine first a quantum version of the perceptron. I put the quantum version of the perceptron here. Then on top of the quantum perceptron, we can build the quantum artificial neural networks, and we can perform the version, like a quantum version of SGD. And for the design of quantum ANN, there are many questions. What type of ANN states we will use? How can we implement some sort of quantum memory for the states? People talk about reservoir processing. Right? They say, oh, even if we cannot fully control this quantum perceptron, can we at least have a network that performs some quantum information processing that that provides relevant augmented features for our input. And when we are more realistic in terms of technological achievement, in terms of quantum computation, people often discuss the development of classical ANN that are inspired by quantum ANN, so that, for example, you can implement some sort of stochastic or fuzzy logic. Okay. And of course, quantum AI would be the higher level, right? So from deep learning to machine learning to AI. And there are many other topics that we can expect to study in the class. So a little bit on the class organization now. So a little bit of a disclaimer here. So this is my first time teaching the class, which it's a regular occurrence for me. We always try to teach new classes so that we become better teachers and have a more varied teaching offer. So that's okay. So it's the first time that I teach at this university. So that doesn't happen so often. The first time that I teach in Italy, although I'm Italian, I never taught in Italian, and I never taught in Italy. And also for me, it's the first time teaching in a Western university, because usually I'm based in Taiwan, and Asian students are very different from Western students. So some of my aptitudes in teaching, or the way I develop my teaching method and my teaching approach, is for generally a different population of students. But I see this as a half full cup, right? So since it's a new challenge for me, that provides a lot of enthusiasm. So I'm really looking forward to the interaction with the students and understanding how you guys think, how you see the world, what motivates you, what is the general scope of your interest, of your background, of your preparation. Very good. Disclaimer number 2. I don't have a control over the background of the students generally. I think we set some background requirements, but of course, everybody has different preparation. And so let's just say that I'm always hoping to change the schedule of the class to accommodate the different backgrounds. So if you want to do more quantum computation, if you want to do more machine learning, if you want to do less Python, more Python, everything is up for discussion. Frontal teaching is sometimes boring and inefficient. So often I'm happy to record the class, make the class available as a video, so that we can work together in class on solving problems or writing code. That's perfectly fine with me. And then Python, right? So I expect to do a few tutorials on Python, so that we can sit down and really do some of these quantum simulations together, see this QSIC software that IBM has developed. And you might think that if you don't have a background in Python, then the class doesn't work for you. But this is not the case, because now that we have Copilot and ChatGPT, coding, it's a very different business. So when one codes using these AI tools, one is more often thinking of the logic of the program rather than the definition of the functions or some of the specifics of the programming part. And then we will go through this because we will go through this QSIC together. So this is an IBM simulation software for quantum computers, and I really want to spend some time really figuring out the specifics of quantum simulations. So the class organization is as follows. We start in the mid of September, and we have 9 classes together. My current idea is to have 2 hours of frontal teaching. I'm sorry for you. I don't know if I could stand 2 hours of hearing myself talk. Then we will do a 15 minutes break, and then there will be another hour of active teaching. The idea is that we have 9 classes, right? So we will have 1 machine learning tutorial, 1 deep learning tutorial. Then with all the other tutorials will be in QSIC. And then we will have a class project, which is in 3 phases. Let's see what are the 3 phases of the class project. Phase 1, each student will present a topic that they think is of interest to them, related to the class, not related to the class, from a paper, from personal interest, from personal experience. It doesn't matter to me. In phase 2, the students will naturally form groups of size between 3 and 5. And then inside the group, the students will coalesce to a certain idea, will present to the class what they want to develop. They will give us some work packages and divide and tell us how they plan to address these work packages and how they're going to divide the work. And in phase 3, there will be after the class is over, and the students will deliver this class project that they have chosen for themselves. Yeah, so in this phase, I hope that this class project will work well. As I said, I don't have a good grasp on the abilities of the students to cooperate together, to communicate, all this set of soft skills that students should have, but most often don't. I hope that everybody in the class will have the independence to address the class project in a satisfactory manner. We are not here, especially at this PhD level, we are not here to give grades. We are not here to give homeworks. We expect that the students naturally will have a drive to learn new things, and I'm sure that this is what's going to happen. And then class evaluation, of course, will be based, will go through the different phases, and the students will evaluate the students mostly. Of course, I will also give my evaluation, but for the students, we will give out some Google Forms, and you will be asked to evaluate your classmates. And we will use this overranking system, where 1 is the worst possible project that you've seen, 10 is the best possible project. And if you have 5 groups, then you will be given a ranking between 1 and 10, and you can rank the group between this number 1 and 10, meaning that you can have rankings, let's say 1, 7, and 10, or 1, 2, and 3, or 9, 8, and 10, meaning that you will have more ranks than groups, so that the gap in between the rankings will tell us something about the difference in quality of the presentation. Okay, so basically it's a scoring 1 to 10. but we don't want to have repeated grades because in our experience, then students will give 10 to everybody, or they will just not pay attention to the grading. So this is the type of scores that we have. And basically that's it. Yeah, so if you have any questions, feel free to write me an email. It's going to be in the poster presentation that I will distribute. I'm looking forward to see you in class. If you want to write to me and tell you what is your background, I will know a little bit how to adjust the class. As I said, I'm usually pretty open to discussion and changes regarding the class format. And otherwise, thank you so much for watching the video so far. And I hope to see you in class in the middle of September. Okay? Ciao, guys.